A resistive circuit contains only resistors and sources. So you can have voltage sources, current sources, or various resistors connected. Since the voltage and current sources are constant, we'll have constant voltages and currents throughout the rest of the circuit. We can use Norton and Thevenin equivalents, we can use nodal and mesh analysis to find voltages and currents anywhere else in the circuit. The thing is, with this type of circuit, the voltage and the current through each resistor is always proportional to one another due to Ohm's law, so any changes in the circuit due to adjusting a resistance or opening or shutting a switch will create what is essentially an immediate response, an instantaneous reaction where all of the voltages and currents will realign and will adjust each other to the new circuit. If we have an RL circuit is essentially a resistive circuit with the addition of an inductor, hence the L in RL circuit. Note that the characteristic equation for the inductor is this, where the voltage across the inductor depends on the derivative of the inductor current or the rate of change of that current. The inductor has magnetic flux inside of it, and whenever the current in that inductor changes, that change in magnetic flux induces a voltage that pushes the current through it and keeps that current flowing. This induced voltage, therefore, causes a slow, continuous change in current as the RL circuit reacts to its new equilibrium. So it has equilibrium before and after these changes to the circuit, but there is what's called a transient response, which is a period of time after the change has been made. And so the circuit evolves from a previous equilibrium to a new equilibrium, and the transient response is the behavior of the circuit as it adjusts from one equilibrium to the other. A inductor cannot produce its own energy. It can only store energy from other sources and then release that energy. Whenever we have a transient response, this transient response is essentially the decay of the finite amount of energy in the inductor. As long as the inductor has energy in it, it can be pumping out that energy, trying to minimize the change in current as much as possible. But eventually, the energy inside the inductor is exhausted, and the current and the circuit settle into their new equilibrium. The voltage across a capacitor is given in the characteristic equation for a capacitor. At equilibrium, the implication is that the current should be a constant amount. That's what it means by equilibrium. It means that nothing is changing. If the current is constant, then the derivative of that current should be zero, and thus the voltage across an inductor should be zero. That means that the inductor is acting like a short circuit, just a piece of wire. In many of these circuits, you'll see it said that the circuit has been in a given state for a long time. For that long time, it means that we are well past the length of time that describes the transient response. The transient response has already occurred after a long time has elapsed, and the circuit is now at its new equilibrium. How we define a long time depends on the inductance and resistance found in the circuit, depends on each individual circuit, but typically we'll say it's about 5 time constants. And we'll see how to define the time constant tau for the circuit, but usually this is a few seconds or less, oftentimes some milliseconds, which is a very short amount of time for us, but could be a little bit longer time in terms of electronics. The inductor has to have some external sources to provide its energy, and so the inductor has to be connected to some circuit. This is the old equilibrium, before some time t0, where the switch opens and the inductor is isolated. So our inductor, at equilibrium, we said acts like a short circuit, it acts as a wire. So we actually have our inductor right here. We're just modeling it as wire because that's how it's behaving. The inductor is connected to some power in the circuit, and so if there's some voltage from this external circuit, there's going to be a current flowing through that inductor, and we'll call that current I0. It's the current flowing the instant, there'll be flowing a constant amount of current through the inductor, and it's the current flowing the instant that the switch opens. If we have a constant current in the inductor, then we have a constant amount of energy stored in the inductor. The total energy depends on the inductance of the inductor, which depends fundamentally on the geometry of the inductor, and it depends on the current that we have flowing initially. But these are both finite values, so this is a fixed value that we have to start with. Since the inductor is acting like a short circuit, this resistor shorted out, so there's no voltage across the resistor, there's no current flowing through the resistor. All of the current from the circuit is just flowing through the inductor and back out. We said that the inductor was connected to the circuit for a long time, and so it was in an old equilibrium where the inductor was acting like a short circuit, and then at some time t equal t0, the switch opens here, and the inductor is isolated from the charging circuit. And so the inductor has a current flowing through it, and in fact, this current is going to be continuous. The current in the inductor is the fundamental quantity that describes the behavior of the inductor, and when the inductor is cut off from its power source, we have energy stored in the inductor, and the dissipation of the magnetic field inside the inductor is going to induce a voltage which is going to push current through. Essentially, the dissipating magnetic field is going to try to keep the current up and keep this current flowing, even though the source of that current has been eliminated. So we had a current I0 at t0 negative, so just the instant just before t equals 0, the instant just before the switch opens. And the current in an inductor has to be continuous, so that means that the instant at t0 plus, that's just barely after t0, just after the switch opens, the current has to be the same amount still, because the current has to be continuous. The magnetic field is going to force that current to stay continuous. And so what's going to happen now is that we had current flowing through the inductor before. When we open the switch, there's no more path here. So this current is still flowing, but it can't flow that way because there's no closed current here. So now this current is going to be redirected, and it's going to flow through the resistor instead. There's only one loop for it to go in, and so that current is going to hit the resistor, and it's going to follow this loop now. Also, recall that we'll have a voltage across the resistor. As soon as we cut off the circuit, the inductor is going to try to run the current on its own, but it only has a finite amount of energy, and so that current is going to start falling off. We assume the voltage across the inductor to be in that polarity because the inductor acts like a passive source, And if we have a current flowing up through the resistor, we're going to have a voltage across the resistor that matches the polarity, because the resistor is always a passive element. And so now, since the switch is open and this circuit is isolated, we can ignore this whole part of the circuit, and let's just focus on the inductor and the resistor and analyze what's going on there. So if we analyze the circuit here, we have a voltage across our inductor because we defined the voltage across the inductor as if the inductor is a passive element. If there's only one loop here, the current has to be going through the resistor, and we know that the current always flows into the positive terminal of a resistor. So we can apply KVL here, and we can show that we have a voltage rise across the resistor, and then we have a voltage rise across the inductor, and we're back to where we started, and so we have to have those two voltage rises give us 0. We start by just using our standard circuit analysis techniques, but we want to go back to writing everything in terms of the currents, since the inductor current is what's driving all of this behavior. So the voltage across the inductor can be written in terms of the current through the inductor, and the voltage across the resistor can be written in terms of Ohm's law, so that it's in terms of the inductor current as well. We have, again, just one current flowing through here, so any current we have flowing through the inductor is going to be flowing through the resistor. Note that I0 is the starting value right when the switch is thrown. As soon as the switch is thrown, that current is going to start decreasing, and this IL is a function of time. We can rearrange this equation, move this to the other side of the equation, because we want to solve for the differential term. And if we do that, we get this relationship here. In order to solve this as a differential equation, we have two differentials. We have di and dt. That means we need to put di on the left side and move I over with it. That means we need to put dt over to the other side. And we end up with this relationship here. We see that the current in the inductor is going to change with time. Note that this is negative, so as time goes on, every change in time gives us a negative value, so there's a decrease in current. If we want to find the current at any point in time, we need to integrate both sides. We'll integrate the current side from I0, which is our initial current, to our function of time. We'll have to integrate t from t0, the initial time when the switch is thrown, to some arbitrary time t. So we'll end up with our current as a function of time based on knowing the initial current when the switch is initially thrown. Notice that I've changed my variables. I'm integrating with respect to the scripted i's and scripted t's so that I can plug in I and t later on. If I integrate 1 over I, I'm going to get natural log of I. And when I plug in my two values, I'll get natural log of the I of t minus natural log of I0. If you are subtracting two natural logs, you can take the natural log of one divided by the other instead. And so we can simplify that term together. This all is a constant. We can just leave that up front. If I integrate dt, I just get t, and when I evaluate at the endpoints, I'll get t minus t naught. And so now if I want to solve for I of t, I'm going to take both sides to the power of e. E and the natural log will cancel, and I multiply the other side over by I naught to cancel that out over there, and I end up with this equation for the current in the inductor. Notice that when t equals t0, this is 0, so e to the 0 is 1. When t equals t0, my current is I0, which is what we said it had to be. And then as time goes on and on, this is a exponential decay, so the current is going to be less and less as the inductor is trying to run the current on its own. It uses up its own energy as it does so, and so it can run the current for a while, but it gets weaker and weaker, and the current goes less and less until it eventually goes to 0, and we have our new equilibrium. We can rewrite that equation for the current, writing this as t minus t0 over L over R, or more simply, the way we usually see it is thus. This equation here is assuming that t0 equals 0. That often is the case. We can start the time whenever we want to, so it makes sense for us to start time t equals 0 when the switch opens, but we'll see some examples where we have sequential switching, where we'll have to use a different value of t. This value of tau here is the time constant, and t over tau, and this is the thing in the denominator here, so that is our time constant for a inductive circuit. The bigger the inductor is, the larger the time constant is, because a larger inductor can store more energy, so it takes longer for it to decay. A larger resistance decreases the time constant, because a larger resistance makes it more difficult to push the current, so the inductor has to burn up its energy faster. This is an exponential decay, so the graph looks like this. We start at I naught, and we decay away, and we can say that we're essentially at 0, we mentioned before, when the time is approximately 5 time constants, would be a good estimate for when we're at 0. And when we're at 0, we're at the new equilibrium. We assumed here that we have just one resistor connected to our inductor. If we have more resistors than that, just use the equivalent resistance there. You can combine all of those resistors in series and parallel and have a bunch of resistors here connected as just one equivalent resistance to our inductor. Once we know the inductor current, we know that the inductor voltage is the inductance times the rate of change of the current. That's our characteristic equation for an inductor. The L term is just there. The derivative of the current is going to be I naught, is just a constant. E to the negative t over tau is going to be e to the negative t over tau, and then when you take the derivative of this, you'll get a chain rule 1 over tau coming out, which we can represent there. Notice that the L and the L cancel, and we end up with this equation right here for the voltage across the inductor. Again, the assumption here is that IL is flowing like that the voltage VL is like that. That's how we defined this equation to begin with. And so notice here that the voltage is actually a negative value. It means that the voltage is negative from this polarity, meaning that the true voltage goes plus to minus. That means that the inductor is acting like an active element here. It's giving energy to the current, and then the energy drops through the resistors. We have a energy added to the circuit from the energy stored in the magnetic field, and then that energy is dissipated by the resistor. Also notice that the maximum value of the voltage is going to be this value. When t equals 0, this term is just 1, and so this is going to be our starting voltage. And essentially, if we have I0 flowing through the inductor, when that current is cut off, I0 has to flow through the resistor, and so R times I0 will be the voltage across the resistor at that first instance that the switch opens. If we want to find the power dissipated by the inductor, that's the same as the power that is received by the resistor, and that power from a resistor is I squared R. I squared is just the current from the inductor squared. The I0 will be squared. We get that term. When you square an exponential, you are multiplying the power by a factor of 2. If we want to find the total energy delivered to the resistor, the total energy is going to be the integral for all time of the power. And so we can integrate that, and we get this expression for the power delivered to the resistor, and thus the energy left inside the inductor. This is the starting energy inside the inductor we saw, and then that energy falls off exponentially as the inductor burns up its own energy to keep the current running as long as possible. In calculus, there's a linearization function where you can linearize a function f of x by saying you're taking f of 0, giving the starting point, and then taking the derivative is the change of that function at x equals 0 and multiplying by x. And so essentially this is a y equals mx plus b. If we have the current of an inductor, we can take the derivative and set it equal to 0, and we find the derivative of the current at t equals 0, the tangent line right there, and we can approximate the current of the inductor, thusly giving us a straight line. Notice that this isn't a very good approximation after some time has passed. It really only works around t equals 0, but the reason that we look at this is that we hit the 0, I of L, the current equals 0, when t equals tau. And so if you can measure the current through the inductor, you can estimate what the time constant is without having to fix this as an exponential curve and analyze it mathematically. You can just look at the initial change in the current, and you can extend that down to the x-axis, the horizontal axis, and wherever you're hitting that horizontal axis, that's a good approximation of a time constant if you're looking at an oscilloscope or something like that. So the steps to finding the natural response of an RL circuit is to determine the initial inductor current I0. That's going to be coming from some charging circuit that you have. Then there'll be a switch that'll be thrown, and you have a change in the current. You want to look at the inductor in its new circuit, and you want to find the time constant for that new circuit. You look at the inductance of the inductor, and you look at the net resistance connected to that inductor. Either there'll be one resistor, or there'll be a network of resistors that you'll have to find the equivalent resistance. Then we know the initial current, and so we can plug that value in. We know the time constant, so you can plug that value in, and so you can then say what the current is going to be at all time later on, t greater than 0, so after the switch has been thrown, we know how the inductor is going to behave and how it's going to drive the behavior of the rest of the circuit. Once you know IL, the characteristic parameter, then you can find any other quantities of interest. You can find the voltage across the inductor, the energy delivered to a resistor, anything else that you might be interested in the circuit.